Good day, learners! Welcome to LBV GMath 3-2.1. I am Engineer Peter Benjamin Obiano, your lecturer for this video. We are now starting a new chapter on our discussion on logic. This is the second chapter. For the next 3 videos, we will be talking about tautologies and fallacies. This video is part of our discussion on tautologies and fallacies under Part 3, Logic for General Mathematics. This video will address the most essential learning competency, which is on illustrating the different types of tautologies and fallacies. For our topic outline, first, we will have a short review on truth tables of compound propositions. Then, after that, we will take a look at what is a tautology, contradiction, and contingency. At the end of the video, I hope that we will be able to define what is a tautology, contradiction, and contingency. And at the same time, to show that a proposition is a tautology, contradiction, or contingency. Before watching the video, I highly suggest that by this time, we already know how to construct the truth table of a proposition. This was discussed in LBV GMath 3-1.4. Let's first have a quick review on the truth values of compound propositions. Let's start with negation. Remember that for negation, if the original proposition is true, then the negation will be false. If the original proposition is false, then the negation is true. Again, kindly memorize the different symbols associated with each compound proposition. Next, we have conjunction. Given the propositions P, Q, and the conjunction P and Q, the truth value is shown below. Take note that for conjunction, it is true only if both P and Q are true. So the conjunction is true if P and Q are both true. If either P or Q is false, then automatic the conjunction is false. Then we have disjunction. Given the propositions P and Q and the disjunction P or Q, the truth table is shown below. For disjunction, as long as either P or Q is true, then the disjunction is true. If both P and Q are false, that is the only time that our disjunction is false. Otherwise, it's true. Let's now go to conditional propositions. Take note that for conditional propositions, almost all combinations result into a true statement, except for this one. Again, for conditional propositions, you have two parts, the antecedent and the consequent. The only time wherein the conditional proposition is false is when your antecedent is true and the consequent is false. That is the only time that our conditional proposition will be false. On other instances, it's now true. Lastly, we have the biconditional propositions. For P, if and only if Q, we have our truth table. Now take note, the biconditional proposition for P and Q is true if both P and Q are false or if both P and Q are true. So again, if both P and Q are false, then the biconditional is true. If both P and Q are true, then the biconditional is also true. If P and Q have different truth values, then the biconditional statement is false. Again, kindly memorize the truth table of each compound proposition. Now that we have reviewed the truth values of the conditional propositions, biconditional propositions, and the other compound propositions, let us now define the terms that we will be focusing in this video. First, we have tautology. So what is a tautology? Tautology is a compound proposition that is always true in every possible interpretation. So it means whatever the truth values of the input propositions are, the truth value of the final proposition is always true. So that is a tautology. Now, what about contradiction? Contradiction is the reverse of tautology. Contradiction is a compound proposition that is always false in every possible interpretation. So again, tautology is a compound proposition that will be always true. Whereas for contradiction, that is a proposition that will always be false. Lastly, we have contingency. Contingency is any compound proposition that is neither a tautology or a contradiction. By the way, this chapter will focus on tautologies and fallacies. As an introduction, let's just define what is a fallacy. In order to define what a fallacy is, first let us define what is an argument. An argument is a group of statements that includes one or more premises and only one conclusion. In an argument, the premise is a statement that provides reason or support for the conclusion, while the conclusion is a statement that indicates what the arguer is trying to convince the listener. Now, there are two types of arguments. One is the valid argument, and of course, the other one is the invalid argument. An argument is valid if and only if it is necessary that if all of the premises are true, then the conclusion is true. This means that if all the premises are true, then the conclusion must be true. If the conclusion of an argument is a tautology, then it is valid. On the other hand, an invalid argument is an argument wherein it is possible to have a false conclusion even if all the premises are true. An invalid argument is also known as a fallacy. So this is the definition of a fallacy. We will discuss arguments and fallacies on the third video. For now, we will be focusing on tautologies. Again, going back to our definitions, tautology is a compound proposition that is always true. Contradiction is a compound proposition that is always false. If none of these two were satisfied, then what you have is a contingency. Now, let us solve some exercises. That way, we will be able to familiarize ourselves with the three terms. Let's start with this one. Prove that the proposition P or not P is a tautology. Now, the first step here is to generate the truth table for this proposition. We need to know the truth values of our proposition. The dominant connective here is the one for disjunction. Thus, we will first get the negation of P, and after that, we will get the disjunction of P and not P. So, let's generate the truth table. All right. So, if P is false, then the negation of P is true. If P is true, then the negation of P is false. Now, let us perform this proposition. Let us take the disjunction of P and not P. Okay, let's do that. False or true will give us true. True or false will give us true. As you can see, in this final column, we can see here that the truth value of this proposition will always be true regardless of the truth value of the proposition P. Thus, what we have is a tautology. So since the outcome is always true for any combination, then this given proposition is a tautology. Let's have another exercise. Prove that the proposition P and not P is a contradiction. The dominant connective here is the connective for conjunction. So what we have is a conjunction. Thus, first we will get the negation of P, and after that we will take the conjunction of P and not P. So let's generate our truth table. If P is false, then the negation of P is true. If P is true, then the negation of P is false. Let us now get the conjunction of these two propositions. False and true will give us false. True and false will give us false. As you can see here, the truth value of P and not P will always be false. That is why what we have is a contradiction. So I hope it's now clear what's the difference between tautology and contradiction. Let's go to the third exercise. Prove that the proposition given is a tautology. The dominant connective here is the one for biconditional propositions. Therefore, what we are going to do is, first, we will get the truth value of this conditional proposition, and we will also get the truth value of the second conditional proposition over here. And then after getting the truth values of each proposition, then we can now perform biconditional propositions. We have two propositions involved, P and Q. Therefore, we have four possible combinations for PQ. Again, let's just use the combinations that we have been using for the past videos. Let's start with if P then Q. Our antecedent is false, the consequent is false. Therefore, the conditional proposition will be true. The antecedent is false, the consequent is true. Therefore, our conditional proposition will be true. The antecedent is true, the consequent is false. Therefore, what we have is false. Take note, this is the only combination that the conditional proposition will become false. Lastly, the antecedent is true, the consequent is true. Therefore, our conditional proposition will be true. We now obtained the truth values of the left side proposition. Let's now go to the right side proposition. Let's just cover this part. Now, let us take the negation of Q. False will become true. True will become false. False will become true. And lastly, true will become false. Let's take the negation of P as well. False will become true. False will become true. True will become false. And true will become false. Now, we can now perform this proposition. So this is our antecedent. This is our consequent. Again, true, true will give true. If false, then true will give us true. If true, then false. Again, this is false. If false, then false, we will get true. All right, let's now go to the last part. Let us get the biconditional of these two propositions. For biconditional propositions, it is true if both the two propositions are true or if both propositions are false. All right, true and true will give true. True and true will give true. False and false will give true. And lastly, true, and true will give us true. As you can see, the truth value of the proposition will always be true regardless of the values of P and Q. So regardless of the truth values of P and Q, the biconditional proposition that we have will always give a true truth value. Therefore, what we have is a tautology. Let's go to exercise 4. Prove that the proposition given is a tautology. Okay, what do we have here? We have here a disjunction. This is a disjunction consisting of two conditional propositions. The left side is if P then Q. The right proposition is if Q then P. Let us prove that this is a tautology. Again, let's use the same combinations for PQ. Let's start with this one. So false and false will give us true. False and true will give us true. True and false, again, this is the only time that the conditional proposition will become false. And lastly, true and true, you get true. Next, let us get the truth values of if Q then P. All right, your antecedent is false, your consequent is false, therefore this is true. Your antecedent is true, but the consequence is false, therefore this is false. The antecedent is false, the consequent is true, what we have is true, and both the antecedent and the consequent are true, therefore for our if Q then P, this is true. Lastly, let us take the disjunction of these two propositions. True or true is true. True or false is true. False or true is true. And lastly, true or true is true. As you can see here, regardless of the truth values of the input propositions PQ, the given proposition will always give a true truth value. Therefore, what we have is indeed a tautology. Exercise number 5. Prove that the given proposition is a tautology. The dominant connective here is the one for disjunction. Thus, what we have is a disjunction of P and the negation of P and Q. So first, we will get the conjunction of P and Q, and then we will negate that conjunction, and lastly, we will perform this proposition. All right, let's start by getting the conjunction of P and Q. False and false is false. False and true is false. True and false is false. True and true is true. Next, let us negate these truth values. False will become true. False will become true. False becomes true. And true will become false. Lastly, let's perform this. Let us take the disjunction of P and this proposition. So let us take the disjunction. False or true is true. False or true is true. True or true is true. And true or false is true. Once again, regardless of the truth values of P and Q, the resulting truth value for this disjunction is always true. What we have is a tautology. Let's go to exercise number 6. Determine if the given proposition is a tautology, contradiction, or contingency. The dominant connective here is the one for conjunction. Thus, let us first get the truth value of the proposition to the left. which is a biconditional proposition. And let us get the truth value of the proposition to the right. This one is a conjunction of not P and Q. And lastly, we will be performing this proposition. All right, let us take first the biconditional of P and Q. So again, for biconditional propositions, this will be true if both P and Q are false or if both P and Q are true. Therefore, false and false will give us true. False and true will give us false. True and false will give us false. And lastly, true and true will give us true. Next, let us negate first P. False will become true. False will become true. True will become false. And true will become false. Next, let us take the conjunction of not P and Q. So let's take the conjunction of these two. False and true will give us false. True and true will give us true. False and false will give us false. And lastly, true and false will give us false. We now have obtained the truth value of the left-hand proposition and the right-hand proposition. For the last step, let us take the conjunction of these two propositions. All right, let's do that. True and false will give us false. False and true will give us false. False and false will give us false. And lastly, true and false will give us false. As you can see here, regardless of the truth values of P and Q, what we have is always false. So the truth value is always false no matter what. Therefore, what we have is a contradiction. Again, since the outcome is always false no matter what combination we have, then our proposition, this one, this is a contradiction. Exercise number 7, determine if the given proposition is a tautology, contradiction, or contingency. The dominant connective here is the one for disjunction. Thus, we are going to get the disjunction of P and the conjunction of P and Q. Let us first obtain the truth values for P and Q. False and false will yield false. False and true will yield false. True and false will yield false. And lastly, true and true will give us true. Then, for our last step, let us get the disjunction of P and Q. All right, let's do that. False or false will give us false. False or false is another false. True or false is true. And lastly, true or true will give us true. By observing what we got, as you can see here, this is neither a tautology because our truth values is not all true. This is also not a contradiction because it's not always false. Since this is neither a tautology or a contradiction, what we have is a contingency. In short, if the truth values are combinations of false and true, it's not purely false or it's not purely true, then what we have is a contingency. All right, I hope everything is clear so far. Let's now go to our last exercise. Prove that this and this are logically equivalent. Prove that the conditional proposition if P then Q and the disjunction of P and Q are logically equivalent. Now, there is another application of tautology. Kindly remember this one. Two propositions P and Q are logically equivalent if the biconditional of P and Q is a tautology. So let's say you want to prove that these two are logical equivalents. One way of doing that is by getting the biconditional of these two. And if ever what you got is a tautology, then you can say that these two are logically equivalent. All right, let's prove that. Let's get the truth values first of the left-hand proposition. All right, let's first get the negation of P. False will give true. False will give true. True will give false. And lastly, true will give false. Now let us take if P then Q. Not P is our antecedent, Q is our consequent. All right? The antecedent is true, but the consequence is false. Therefore, this is false. The antecedent is true, the consequent is true, therefore, this is true. The antecedent is false, the consequent is false, therefore, this is true. And lastly, the antecedent is false and the consequent is true. Therefore, what we have is true. So these are the truth values of if not P, then Q. Let us now get the truth values of P or Q. False or false will give us false. False or true will give us true. True or false will give us true. And lastly, true or true will give us true. Now that we have obtained the truth values of the left proposition and the right proposition, let us now take the biconditional proposition right here. All right. So again, let's apply the concept of biconditional propositions. False, false will give us true. True, true will give us true. True, true will give us true. And lastly, true, true will give us true. As you can see, the biconditional of the two propositions is a tautology. If that's the case, we can therefore conclude that this proposition and this proposition are logically equivalent. Though honestly, we just applied the principle. However, if you remember last video, you do not actually need to perform this one. Just observe the truth values, isn't it, that we mentioned in the last video that if two propositions have the same truth values, then they are logically equivalent. Though for the sake of proving the principle, then you can refer to this one. Again, one way of proving logical equivalence is by getting the by implication of the two propositions and then check if it's a tautology. If it's a tautology, then these two are logically equivalent. All right, so we're done with the video. I hope that from this video, we were able to define what is a tautology, contradiction, and contingency. And at the same time, I hope that we were able to show that a proposition is a tautology, contradiction, or contingency. We are now done with LBV 3-2.1a. The next video will be on 3-2.1b. In that video, we will be talking about the different types of tautologies. For additional learning, you can still refer to Quek's book on General Mathematics, Chapter 6. Stay safe and God bless to all of you.